Section 19.6 Rotational Spectroscopy. For a two-particle rigid rotor, I equals mu r naught squared. I is the moment of inertia. Mu is the reduced mass. 1 over mu is equal to 1 over m1 plus 1 over m2. R naught is the distance between the two particles. We use R naught instead of R to emphasize that this R naught is a constant. We have a rigid rotor. The rotational energy is J times J plus 1 times h bar squared over 2I. And also we can define a rotational constant B this way. We simply just write out the rotational energy in this expression, J times J plus 1 times HCB, and B is a constant with a unit same as wave number. So if you compare these two equations, we can cancel J times J plus 1. So B is really h bar squared over 2I over hc, right here. H squared over 2I over hc. H bar is the reduced Planck constant. H bar is h over 2 pi, so we have this B is equal to h over 8 pi squared Ci. And again, h is the Planck constant, c is the speed of light, I is the moment of inertia of this two-particle rigid rotor. The rotational energy levels shown on a high-resolution infrared spectrum can help us obtain the bond distance of the atomic molecules. I'm going to explain a bit later. The selection rule for the rotational transition is delta J is equal to plus minus 1. This is similar as the selection rule for vibrational transition. For vibrational transition, you have delta N equals plus minus 1. For rotational transition, the selection rule is delta J equals plus minus 1. This quantum number J must change by 1. Therefore, each vibrational transition of a diatomic molecule is always accompanied by a rotational transition. And in that rotational transition, J must change by 1. For example, if we are looking at 0 to 1 vibrational transition of HCl, it's always accompanied by a rotational transition with delta J equals either plus 1 or minus 1. Pure vibrational transition of HCl is forbidden and thus never observed in the high-resolution infrared spectrum. So again, this is very important. Okay, so the vibration energy of this HCl changes from 0.5 h nu to 1.5 h nu right here. So the energy change is 1 h nu. But at the same time, this HCl molecule must undergo a rotational transition. It can be excitation or de-excitation. So J may increase by 1 or decrease by 1, but J must change by 1. Now I'm going to give you an example here. So again, let's just imagine this is HCl. So over here, all these lines correspond to n equals 0. See, n equals 0 and then J equals 1. Oh, I'm sorry, J can be 0. So n equals 0, J equals 0. n equals 0, J equals 1. J equals 2. J equals 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'm showing you this 11 energy levels. They correspond to J equals 0 all the way to 10 and 11. But n is always 0. Now let's look at this energy levels. In this energy levels, n is 1. And then J, what's the value of J? J can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12 lines here from 0 to 11, 12 lines. Also here from J equals 0 to J equals 11, there are 12 lines. So what about the vibrational rotational transition of the molecule? Again, you will have to change the value of n by 1. So it's going to be 0 to 1 transition. So you are looking at 0 to 1 transition accompanied by a rotational transition. So let's look at this side. Okay, they have something in common. So if you look at this one, J is 0. Over here, J is 1. So J changes by 1. Okay, over here, J is 1, J is 2. J changes by 1. This is from 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, etc. So on this side, the value of J increases by 1. This is the so-called R branch. This is the R branch. And now let's look at this side. So look at this initial value of J. It's 1. So it's going from 1 to 0. And then over here, J initial value of J is 2. 2 to 1, 3 to 2, 4 to 3. So on this side, the value of J decreases by 1. This is the so-called P branch. So R branch, P branch. What's in the middle? P, Q, R. So in the middle, there's a invisible Q branch. Why it's invisible? Q branch corresponds to delta J equals 0. So this is forbidden. So over here, delta J is negative 1. That's P branch. Delta J is 0. Q branch. Delta J is plus 1. R branch. So that's why in the high resolution infrared spectrum of HCl, you see this kind of pattern. In the middle, there's a gap. This is the invisible Q branch because this is a forbidden transition. The HCl molecule cannot undergo a pure vibrational transition with delta J equals 0. And now over here, this side, delta J is plus 1. This is your R branch. Over here, delta J is negative 1. You can see from 1 to 0, 2 to 1, 3 to 2, the change is negative 1. You're looking at a P branch here. That's why if you have a high resolution infrared spectrum of HCl, you're going to see many, many peaks. Again, in the middle, there's a gap. There's a pure vibrational transition. It does not occur. Oh, by the way, when we are looking at this diagram, I didn't draw any transition from N equals 1 to N equals 0. This is because at the room temperature, due to this large energy gap, the majority of the HCl molecules occupy this N equals 0 level. Nearly none of them occupy the N equals 1 level. Now, the intensity of each peak is proportional to the population in its initial rotational energy level. So we'll have to look at the Boltzmann distribution here. The ratio between the populations in the jth level versus 0 level is Gj over G0 times this exponential function. This is the so-called Boltzmann distribution, e to the power of negative energy difference over kBt. So now, what about this G sub j, G sub 0? Those are the degeneracies. The degeneracy of the 0th level is just 1. The degeneracy of the jth level is 2j plus 1. Why is that? Actually, this G sub j, this degeneracy, is equal to 2j plus 1 because when you have a three-dimensional rotation of a linear molecule with a quantum number j, then its z component can have different quantum numbers. It can be negative j plus 1, negative j plus 2, etc., 0, and then 1, 2, and then j minus 1j. So really it's from negative j to positive j. If you count the different numbers between negative j and positive j, you have 2j plus 1 different values. So in this case, we say, well, the z component of the angular momentum of the rotation of the linear molecule can be negative jh bar all the way to positive jh bar. So there are 2j plus 1 values. The degeneracy is 2j plus 1. This equation gives you the energy difference between the 0th level and the jth level. All right. So you can see negative h bar squared times j plus 1 over 2i. That's the energy of the jth level. E sub 0 is simply 0. All right. We can do quantitative analysis of the high-resolution infrared spectrum of HCl. First, let's look at the energy of the photon. This is the energy of the photon. H nu is hc over lambda, and we use this nu tilde as the wave number. So hc nu tilde is equal to the energy change of the HCl molecule. The change of the energy is the change of the vibration energy and the change of the rotation energy at the same time. So we got these two parts. All right, we got these two parts. And this is the vibrational wave number. And this is the change of the rotation energy. So it's possible for the HCl to undergo rotational excitation or rotational de-excitation. In excitation, J increases by 1. In de-excitation, J decreases by 1. So let's look at these two different formulas. Over here, this is the final energy minus initial energy. The result is here. Well, J can be 0, 1, 2, 3. J plus 1 can be 1, 2, 3, 4. So again, the value of J increases by 1, and the energy change is 2 times J plus 1 times HCB. So this energy change divided by HCB is going to be a even number. It can be 2 or 4 or 6 or 8. You just plug in the value of J here. J can be 0, 1, 2, 3. And then 2 times J plus 1 can be 2, 4, 6, 8. So what does that mean? Well, that means when you do a vibrational transition, it's accompanied by a rotational transition. If the rotational transition is excitation, J increases by 1. And then we need to include this much energy. Either it's 2 HCB or 4 HCB or 6 HCB or 8 HCB. Well, the HCl molecule can also undergo a rotational de-excitation over here. And then you can see after this derivation, the change of the rotation energy can be negative 2, negative 4, negative 6, negative 8 times HCB. So really, the energy change of HCl is H nu plus minus 2 HCB. So that's it. Plus minus 2 HCB. Okay. So now let's look at this formula. This is the wave number of the photon. This is the wave number correspond to the harmonic oscillator. And this give you the rotational energy change in wave numbers. If you multiply this by Hc, you get the energy of the rotational excitation or de-excitation. If you multiply this by Hc, you'll get the vibration energy. If you multiply this by Hc, you'll get the energy of the photon. Right, so again, in the end, if you look at the high resolution infrared of HCl or some other diatomic molecules, you will see many wave numbers. They correspond to the wave number of the HCl harmonic oscillator, plus minus 2b, plus minus 4b, plus minus 6b, plus minus 8b. When you see plus signs, plus 2b, 4b, plus 6b, 8b, that's R branch. If you see minus signs, minus 2b, minus 4b, minus 6b, minus 8b, those are P branch. All right, now, if you somehow look at all those peaks, there are so many peaks, you'll realize that either in the P branch or in R branch, there are many peaks. The energy spacing is 2b, or I want to say the spacing between two adjacent peaks is 2b. All right, and then you divide that by 2, you get the value of b. All right, and then once you have b, if you have the value of b, and then you look at this equation, you will be able to get I. Once you have the moment of inertia, you will be able to determine the distance between the two particles. For HCl molecule, you will be able to determine the bond distance. Now I want to show you those wave numbers, graphically. So this is the wave number correspond to the vibration. Plus minus 2b, plus minus 4b, plus minus 6b. Those are rotational excitation and de-excitation. So I want to show you the infrared spectrum here. Alright, so this over here, around 2980, around here, this is pure vibrational transition, pure vibrational wave number. And then plus 2b, you get this one, plus 4b, you get this one, plus 6b, you get this one, plus 8b. Alright, so this two differ by 2b, this two differ by 2b, this two differ by 2b. Okay, and then we can go left. Again, this is pure vibrational transition wave number. Alright, and then you can go this side, minus 2b. This one is pure vibrational transition, minus 4b, minus 6b, minus 8b, minus 10b. So this two, okay, this is vibration minus 2b. This is vibration minus 4b. The difference is 2b. So basically, you just measure this difference. The difference is equal to 2b. What about this two? They differ by 2b. They differ by 2b. So you just measure this and divide that by 2. You get this rotational constant b. Once you have this b, you plug in this equation. So this is the equation. This is how we define b. You will be able to obtain the value of I easily. I is the moment of inertia. I is mu times R naught squared. So I want to show you that equation here. I is mu times R naught squared. And how do you get I? Again, use this equation. I is just h over 8 pi squared cb. So this is how you get I. And then again, once you get I, you will be able to get mu naught. We can also just write out the whole equation. So R naught squared is just h over 8 pi squared cb mu. You just move this mu here. And then you take the square roots. You get this nice equation for the bond distance of a diatomic molecule. All you need to do is plug in the value of the Planck constant, speed of light, rotational constant. You get this from the high resolution infrared spectrum. You can pick the R branch, you can pick the P branch. Just measure the difference between two adjacent peaks. That's 2b. So divide that difference by 2, you get b. And mu is the reduced mass. Let's look at the mu of HCl. 1 over mu is 1 over the mass of hydrogen plus 1 over the mass of chlorine. I want to say 1 over the mass of hydrogen is much greater than 1 over the mass of chlorine. So 1 over mu is roughly 1 over the mass of hydrogen. So I'm making some approximation here. I'm going to say, well, it's really the value of mu is very close to the mass of hydrogen, which is 1.0 AMU. So we can just do this. And if you do this calculation, I think it's roughly 1.6 something times 10 to the power of negative 27 kilogram. Be sure you use kilogram. Kilogram is the SI unit of mass. And then if you measure B for HCl, I think it's around 10 wave numbers, or one wave number is 1 reciprocal centimeter. And this means 10 waves within this 1 centimeter. So the wavelength is actually 1 millimeter. So within 1 centimeter length, you can put 10 waves there. And we'll convert this to SI unit. So if each wave has a wavelength of 1 millimeter, and then we can put 1,000 such waves within a length of 1 meter. So again, when you do this conversion, pay attention here. This is 10 per centimeter. 10 per centimeter is 1,000 per meter. Okay, now we have all the numbers we have. This is Planck constant, 2 pi squared times the speed of light, and this part is the rotational constant B in the SI unit. And over here, this is the reduced mass of HCl. You get 1.3 angstroms. And this is the bond distance of HCl. Well, of course, I'm just making approximations. You can get more accurate data. I think this is 6.626, right? And I think this is 2.9979. And I think you can get a more accurate value for B. And over here, the reduced mass of HCl is slightly smaller than 1.0 AMU. And I believe if we convert it to kilograms, I think it's going to be roughly 1.60 times 10 to the power of negative 27 kilograms. So if you use more accurate values in here, I think you will get a more accurate result. It's going to be actually 1.275 angstroms, or 1.275 times 10 to the power of negative 10 meters. So again, this is how chemists measure the bond distance for a diatomic molecule.